Welcome to GenAI Kitchen, where our mission is to educate, inform, and demystify the world of AI. We bridge the gap between technology and business, making AI accessible and transformative across all industries. Whether you are a business leader looking to optimize operations or a developer eager to unlock AI's full potential, we offer tailored solutions that drive efficiency, spark creativity, and solve real world challenges. Now that you know what we are about, let's dive into today's session. You say you're ready for AI. So let's walk you through the evolution from traditional software to generative AI. In today's world, everybody is talking about artificial intelligence, machine learning, and generative AI. But what do they really mean? How do they impact your business, your career, or even your day-to-day life? In this video, we are going to strip away the jargon and demystify these buzzwords, showing you the real power of AI and how you can leverage it. Whether you're a developer, a business leader, or just curious about the future, let's dive in and unlock the true potential of AI together. It's now time to cut through the noise and tackle the buzzwords head on. Traditional software, AI or artificial intelligence, machine learning, traditional AI, deep learning, discriminative AI, generative AI. Everyone's talking about them. But what do they really mean for you? Whether you are navigating business decisions or exploring new tech, understanding these terms is key to unlocking their true potential. In the next part, we are going to break down these concepts and show how they are reshaping industries, careers, and everyday life. Ready to dive in? Let's move on. Picture this. Back in the day, you would visit Madame Zaza, peering into her crystal ball, hoping for a glimpse into your future. Her predictions were all about intuition, guesswork, and a little bit of luck. Fast forward to today, and instead of crystal balls, we got AI and machine learning doing the heavy lifting for our predictions. So how is Madame Zaza's crystal ball, our stand-in for traditional software, different from AI? Alright, let's break it down. Traditional software. Think of it like Madame Zaza's crystal ball. It only shows you what it's being told to show. It follows a strict set of rules, step by step, doing exactly what it's being programmed to do. No surprises, no creativity, just predefined actions. Examples? Classic stuff like Word, Excel, web browsers, calculators, or even early video games like Tetris or Super Mario, where every move is hard-coded into the system. It's reliable but rigid. On the other hand, AI is a whole new ballgame. Imagine a crystal ball that just doesn't spit out the same old predictions. It gets smarter every time it gives you an answer. AI learns, adapts, evolves based on the data it's fed. In tech speak, AI refers to machines performing tasks that usually require human intelligence, like decision making, problem solving, or even understanding natural language. Think of chatbots like Siri or Alexa, where it sets reminders or play music based on your voice commands. Or robots in factories assembling products with precision. AI can handle anything from simple rules to complex evolving tasks. But here's where it gets really interesting. Enter machine learning. This is where things start feel like more futuristic. ML is a subset of AI. It's all about computers learning from data without being explicitly programmed for every little task. For example, Netflix doesn't just offer random shows. It learns from what you have watched to recommend what you probably would enjoy next. Or your email spam filter, where it learns from past patterns to block junk before it hits your inbox. Now let's roll up our sleeves and dive deeper. What's really going under the hood with ML-driven systems versus non-ML-driven systems? Let's take a closer look. In simple terms, with traditional software, you tell the computer exactly what to do. With machine learning, we teach the computer how to figure things out on its own using the data we give it. Instead of hard coding all these rules, we let the machine learn patterns and make decisions based on what it's learned. For example, imagine trying to forecast the weather with hundreds of different factors like temperature, humidity, wind speed, and so on. Instead of manually figuring out how all of these factors are related, you can feed historical weather data into the machine learning model, and it will learn the patterns and come up with its own rules to predict the future. Pretty cool, right? But here's the key question. What kind of data does the machine need to learn effectively in an enterprise setting? In an enterprise application, having your data ready is like fueling rockets for launch. Machine learning models thrive on diverse data and are shaped by the problem they're designed to solve. Whether it's images, videos, text, or structured business data, it's not just about having data, it's about having clean, well organized, and properly labeled data. Without that, your rocket might never leave the ground. Let's dive into the key steps of data preparations that enterprises need to put in place and why this foundation is crucial for successful machine learning deployments. Let's now break down the key factors for getting your data ready for machine learning, because no one wants the data to be a mess. First up, data location. First, you need to know where your data lives. If it's scattered across several servers, databases, or cloud storage, it's like trying to find your keys in a messy house. Organizing your data is essential for smooth machine learning operations. No one wants to be stuck with data puddles everywhere. Data quantity. When it comes to machine learning, size does matter. The more data you have, the better your model will be at spotting patterns. Think of it like trying to learn a language. You will pick it up faster if you hear lots of examples. So get those data buckets filled up. Next up, data security. Protecting your data is non-negotiable, especially when it's sensitive. Whether it's your personal information or business secrets, security is the key. No one wants to turn their customers into toads. Keep that data safe. Next up, data diversity. It's not just about having a lots of data. It's about having the right mix of data. If you're only feeding your model one type of data, it's like feeding a dog the same kibble every day. It gets boring fast, really fast, and your model won't learn as well. So mix it up. And finally, data quality. Quantity and diversity are great, but if your data is messy, it's like trying to bake a cake with expired ingredients. Clean, accurate data is what makes your model work well. Remember, garbage in, garbage out. So keep that data fresh. In the end, you want your data to be more than just a collection of puddles. It should be clean, organized ocean that powers your machine learning rocket. Now that you covered the importance of getting your data ready, let's dive into how traditional machine learning uses the data to make predictions. In traditional machine learning, we train models to recognize patterns in data and predict outcomes based on those patterns. It's kind of like giving the model a bunch of examples and letting it learn the rules by itself. Once it figures out the pattern, it can make predictions on new data. Here's how it works. Let's use ice cream sales plot as an example. Training the model. We feed the model historical data. In this case, past temperatures and corresponding ice cream sales for two groups, kids and adults. The data points for kids, which are blue circles in the plot, and adults, green crosses, represent the actual sales numbers at different temperatures. The model takes all of this data and start to analyze its patterns. How do they learn the patterns? As the model studies the data, it learns the higher temperatures generally lead to more ice cream sales, but for both kids and adults. It uses this relationship to come up with a formula represented by the red line and describes how sales are expected to change with temperature. The key here is that the model doesn't just memorize the data, it finds the underlying pattern so it can apply it to new situations. And how does it make the predictions? Once the model has learned this pattern, it can use it to predict the future sales based on the temperature it has never seen before. For example, if the temperature tomorrow is 92 degrees Fahrenheit, The model can predict how much ice cream will be sold to both the kids and adults. The red line represents the model's best guess at what sales will be based on the temperature. Dealing with more complexity, this process can get more complex when you introduce more variables. For example, we can add factors like humidity, time of the day, or whether it's a weekend or a weekday. The model can take into account when making these predictions. This flexibility is what makes machine learning so powerful. It can handle variables and learn from them simultaneously. The algorithm used here is called linear regression, which is one of the simplest and most common machine learning techniques. It works by fitting a straight line through different data points that minimizes the error that the actual sales and predicted sales. In this case, the model doesn't treat kids and adults differently in terms of learning the pattern. More complex models like decision trees, random forests, etc. are available that might handle both the groups separately. Congratulations! We just covered a class of models called supervised regression. Now that we have seen how the model learns patterns and makes predictions, it's time to connect the dots. Just like the turkey on this slide, regression models use past data to predict the future outcomes. The turkey predicts steady weight gain based on previous trends, assuming everything will continue smoothly into December. But what it doesn't know is that Thanksgiving is coming and that the growth pattern might hit an abrupt stop. This reminds us of something important about supervised learning. It works great when things stay predictable, but it can miss those unexpected changes, just like our earlier ice cream sales example. Remember that ice cream sales model? If that model has only seen sunny days, it might predict more sales as temperature rises. But what if we suddenly have a rainy day? Without that rainy day data, the model might keep predicting high sales, just like the turkey's steady weight gain prediction. In both the cases, the model prediction would miss a key factor: rain for the ice cream sales or Thanksgiving for the turkey. The lesson here: supervised regression models rely on the data they are trained on, and unexpected events can throw them off if they are not part of the training data. Now that we have covered linear regression, let's move on to another type of algorithm. Just like before, we use data to train the model to make predictions. However, instead of predicting continuous values like sales amounts, this algorithm is used to predict binary outcomes. In this case, whether someone will buy ice cream or not. Here's how it works. Use our ice cream sales example. We feed the model historical data, temperatures, and whether kids, blue circles, or adults, green crosses, bought an ice cream, 1 for yes and 0 for no. The model takes all the data and starts analyzing it to understand the relationship between temperature and likelihood of buying ice cream. The model learns that as the temperature rises, the chance of someone buying the ice cream increase. It doesn't just memorize the data, it learns the underlying pattern and maps out the probability of purchase at a given temperature. The red curve shows this. It's the model's best guess of the probability of buying an ice cream as the temperature change. Once the model has learned the pattern, it can now make predictions about new unseen temperatures. For example, if tomorrow's temperature is 85 degrees Fahrenheit, the model can predict the probability that both kids and adults will buy ice cream. The red curve shows that the likelihood of buying ice cream increase as the temperature goes up. To deal with more complexity, this model combines the data of both the kids and adults into one prediction. But just like with linear regression, the process can get more complex. If you want to include more variables like humidity, time of the day, or special events, we could build more sophisticated models to handle these two variables, improving the accuracy of our predictions. The type of the algorithm you use for predicting binary outcomes like yes or no or to buy or not to buy. In this case, the model combines data of both the kids and adults to predict the probability of buying ice cream based on temperature. If we needed to separate these two groups, more advanced models like decision trees or random forests could handle it. With this approach, we are not just predicting a number, but the likelihood of an event happening based on the patterns we have learned from the data. We just addressed another class of models, supervised classification. And what better way to explain it than Santa's annual classification system? Naughty, nice, or neutral? Just like Santa on this slide, classification models use labeled data from the past to predict which category a new input, in this case the child, belongs to. Santa's decisions are based on past observations. Has the child been good, bad, or somewhere in between? This reminds us of an important point about supervised classification. It's all about sorting new data into predefined categories based on patterns learned from labeled examples. Remember our earlier ice cream sales example? That was a binary classification problem. Yes or no to buying an ice cream. But classification can involve more categories like Santa's naughty, nice, or neutral. Just like Santa relies on past behavior to classify kids, supervised models relied on past data to make decisions. And that's why it's called supervised. The lesson here, whether you're a kid visiting Santa or data entering a machine learning model, the principle is the same. Learn patterns, determine the category. Here's a quick visual recap of supervised learning. In this example, the training data consists of labeled images of apples and bananas. The machine learning model is trained on this data, learning the patterns that distinguish apples from bananas. Once trained, the model can take in unseen, unlabeled data like a new banana and classify it as banana based on what it has learned. This perfectly illustrates the idea behind supervised learning. The model is trained on labeled examples, apples and bananas, and uses the knowledge to make predictions on new unseen data, a green banana. The entire process depends on supervision provided by the training data, which tells the model what the correct answer should be. In summary, the supervised learning teaches the model using labeled data, and once trained, it applies these learned patterns to classify new data. Here's an interesting challenge. Looking at this object, how do you think the model would classify it? If our model was only trained on apples and bananas, what happens when it encounters something completely new, like this mystery object? The model might try to classify it as either apple or a banana based on patterns it has learned. But here's the catch. Models can only classify data based on what they have been trained to do. If they haven't seen anything like this before, they might get it wrong. They will get it wrong. In this case, the model might confidently classify this as banana. Why? Because it only knows apples and bananas, and the shape of the object resembles a banana in this model. This illustrates a key limitation of machine learning models. Models will force unfamiliar data into familiar categories. That's why diverse training data is essential to building accurate, reliable models. Now that we have explored how important it is for models to learn from labeled data, here's the next big question. Is your data labeled? As this meme humorously points out, data scientists often get excited about new machine learning projects. But then comes the reality, data labeling. Labeling data can be very time consuming, but it is absolutely crucial for supervised learning models. Without labeled data, the model has no reference to what's what. So what happens when you don't have labeled data? This is where we move on to a different approach, clustering. In clustering, we use unsupervised learning. where the model isn't given labels. Instead, it looks for natural groupings or patterns in the data, even when we don't explicitly tell it what's what. Next, let's dive into how clustering works and how models can group data without needing labels. In unsupervised clustering, the model groups data based on similarities it finds, but it doesn't know what these groups represent. For example, it might create cluster 1 for long curved objects and cluster 2 for round objects. But the model has no idea that cluster 1 is bananas and cluster 2 is apples. It's just looking for patterns and grouping similar items together. Once the model forms the groups, it's up to us to find out what these clusters mean. We, the humans, have to look at the groups and say, these cluster means bananas and this cluster means apples. Some real world examples: customer segmentation. A business might want to group its customers based on behavior. The model might group people who shop frequently into one cluster and occasional buyers into another cluster. But it wouldn't know which is which. This is where we step in and label them as loyal customers or infrequent customers. Other example is image grouping. If you have a massive photo library, the model might cluster different pictures or images together with similar colors and shapes, like sunsets in one group, cityscapes in another. But it is up to us to recognize how to label these clusters as sunsets or cityscapes. So the model does the heavy lifting of creating these groups, but we are the ones who give meaning to these groups by figuring out what they actually represent. Now that you have seen how clustering works and how model groups data based on patterns, let's take things up a notch. What if we want a model that not only groups data or makes predictions based on basic patterns, but can actually learn complex relationships all by its own, like recognizing faces in photographs or understanding speech? This is where deep learning comes in. Unlike traditional models that rely on simpler patterns, deep learning models can actually handle massive amounts of data and learn deeper, more complex features all by themselves. Think of it as a model that doesn't just group apples and bananas, but can also tell you if it's a red apple or a green apple. Deep learning uses a type of a model called neural networks, which are inspired by how our brains work. These models can learn from raw data, figure out complex features, and make predictions that are far more sophisticated than traditional models. Ready to see how these deep learning models work? Let's dive in. Imagine a model that has never seen a panda before, but can learn what one looks like piece by piece, layer by layer. Deep learning is like teaching a toddler what a panda looks like. You start by showing some basic pictures. Look, here's a panda. The toddler might not understand it at first, but as you show more and more examples, they start recognizing the round ears, fluffy fur, and the black and white patterns. Similarly, deep learning models are like layers of learning, where each layer builds on the information learned by the previous one, in a step-by-step process that gradually helps the model understand more and more complex features in the data, whether it's images, text, or sound. Let's take our panda example and see how this works. Layer 1. Basic shape detection. The first layer is super simple. It detects the most basic features like the lines on the panda, the edges on the panda, or the color patches, in this case black and white. It doesn't know what it's looking at. It's just analyzing the building blocks of the image. Layer 2. Patterns and texture detection. Now things get more interesting. This layer takes the simple shapes from layer 1 and starts identifying patterns and textures, like the fluffy fur or smooth areas of the panda. It passes this richer information to the next layer, body parts detection. By now, the model is starting to recognize more defined features like ears, eyes, or the overall round shape of the face. The pieces are coming together, but the model isn't ready to make a final call yet. It passes this understanding to the next layer, larger parts detection. This is the final stage where the model begins to see the bigger picture. Literally, it starts recognizing larger parts like head or arms and begins piecing them together. It's now ready to ask the big question: is this a panda? Here's the really cool part. Each layer passes its findings to the next layer, making the model understanding deeper with each step. But it doesn't end there. Once the model makes a prediction like this is a panda, and again remember it's a supervised training where there is a labeled information. When it asks if it's a panda, it's checking against the label which is predefined. It checks if the prediction is right or wrong. If it is wrong, the feedback is sent back to the earlier layers, telling them to adjust their understanding. So every time a model makes a prediction, it learns from its mistake. This feedback loop is what helps deep learning models become more accurate over time, layer by layer. It keeps learning and refining its knowledge until it can confidently say, yep, that's definitely a panda. Deep learning layered approach is what allows these models to take on complex tasks like recognizing faces, detecting objects, or even driving cars. In conclusion, while deep learning models have the incredible ability to process large amounts of data and pick up on intricate patterns, they still have a way to go before they match the quick learning capabilities of a toddler. A child can learn from just a few examples and generalize across different contexts, whereas deep learning models often need like thousands of images to reach a similar level of understanding. However, where deep learning shines is in its capability to handle vast data sets and continuously refine its understanding over time. As technology advances, the gap between human and machine learning is narrowing. But for now, there is still something special about how effortlessly toddlers can learn. So while deep learning methods or models may be powerful, they're still learning from us in more ways than one. Now let's dive into what happens inside a layer of a deep learning model. And we will start with the idea of neurons. Imagine neurons in a deep learning model as a tiny decision maker or worker in an assembly line. Each worker, neuron, has a specific job. Some might be looking for certain patterns like lines or colors, while others might be on the lookout for more complex features like shapes or textures. But here's the twist: every worker's decision isn't equally important. How strongly a worker's opinion or a signal matters is determined by something called weights. So, how do neurons work? Picture neurons like light switches, but not just like those on off switches. They are more like dimmers that can adjust on how much light or signal they can send. Every neuron fires, but how bright it shines or how strongly it signals depends on its weight. Here's a simplified analogy. Strong signals, like a bright light, comes from neurons detecting something very important, like black fur on a panda. Weak signals, like a dim light, comes from neurons picking up less important details, like a tree in the background. Now, the interesting part, the weights. Think of these as dials that adjust how each neuron's opinion counts. If a neuron detects something critical, like pandas' distinct round ears, the weight dials up, making its signal louder. But if it picks up on something less relevant, like a random shadow, the weight might dial down, so its signal is softer. The coolest part? Neurons learn over time. When the model makes a mistake, let's say it misidentifies a raccoon as a panda, the model gets feedback and goes back to adjust the weights. It's like telling a worker in the assembly line, hey, you put on too much importance on this detail. Next time, dial it down. Over the time, the neuron gets better at their jobs. Start making more smarter decisions. Imagine you're showing a model different pictures of pandas. Neuron A is looking for black fur and notices a lot of it, so it fires strongly. Neuron B is looking for round shapes, maybe the ears, and fires, but not as strongly because it only sees a few curves. Neuron C is watching the background, say some trees, and it fires weakly because it knows the trees aren't as important in identifying the panda. Once these neurons combine their signals, the model decides, yes, this is a panda. But if it was strong, the model adjusts, telling the neurons to dial up or dial down their signals next time. Neurons fire based on what they detect, but how much they contribute depends on their weights, which are fine-tuned through feedback in the process of supervised learning. By learning from labeled examples, the model improves over time, adjusting its neurons and getting better at making accurate predictions. Is like having a team of workers getting smarter with every task they complete. Now that we have explored the broader AI and machine learning landscape, let's zoom in on discriminative machine learning and where it fits. Discriminative ML is all about making predictions. Based on the input data, they are learning to distinguish between categories or predicting values. Whether we are using traditional algorithms like logistical regression or linear regression, or more complex models like neural networks, discriminative models focus on learning the direct relationships between inputs and outputs. In classification, discriminative models figure out the boundary between the categories, like determining whether an image is a panda or a raccoon. In regression, they predict continuous outcomes, like a forecasting house prices based on input features. In both cases, the model isn't concerned with the underlying data distribution. Instead, it's focused on finding the patterns that help it make accurate predictions. Now that we have covered discriminative machine learning, let's address a common question. Can we replace traditional historical analytical systems with machine learning? Here's the short answer. It depends on the task. Traditional analytical systems are great at dealing with structured, well-defined problems where the relationships are already understood. They rely on rules and established formulas, which makes them highly reliable for tasks like generating financial reports or calculating inventory levels based on fixed rules. Where ML steps in? However, machine learning excels when you are dealing with complex unstructured data or when relationships between variables are not easily defined. ML can adapt to new patterns as data changes over time, find hidden relationships in data that traditional methods might miss, handle vast amount of data, and make predictions even when the rules aren't clear. But it's not always about replacing historical systems. It's about augmenting them. For tasks that require adaptability and pattern recognition, like demand forecasting or fraud detection, ML can provide a big advantage. There are specific scenarios where ML can outperform traditional systems and some where the two might work together. Next up. Now that you have touched on potential of replacing traditional systems with machine learning, let's get into a common question. Are you hoping for 100% accuracy for these ML models? The truth is, when it comes to machine learning, expecting 100% accuracy is often unrealistic, and here's why. Data is never perfect. Real-world data is often messy, incomplete, and noisy. There will always be anomalies and outliers that can throw off predictions. So ML models aim for high accuracy, but 100% isn't actually achievable. Complexity of the task. The more complex and dynamic the problem is, the harder it is for a model to consistently get every prediction right. Even humans are not 100% accurate when making decisions. The role of improvement. Machine learning models are built to learn and improve over time. The key is not aiming for perfection from the start, but striving for continuous improvement and refining predictions as more data is processed. So, while we don't expect 100% accuracy, the goal is to develop models that are highly reliable and capable of improving as they encounter more data. It's about finding the sweet spot between the performance and practicality and not chasing perfection. Let's now shift gears and introduce an exciting new topic, generative AI. And this is probably the reason why most of you are here. Unlike traditional machine learning models that are focused on classification or prediction, like identifying a panda or forecasting sales, generative AI, a subset of deep learning based on transformer architecture, does something completely different. It creates. Whether you're generating an image, music, audio, or even video, generative AI learns from data they have been trained on and use that knowledge to produce new content that didn't exist before. Think of it as AI's creative side. We are now entering a world where machines can help us generate new ideas, art, or even fully functional code. Let's deep dive into how generative AI works. Its real world applications and why it's becoming such a game changer in the AI world. All right. We have covered three different ways to code with machines: traditional software, discriminative ML, and generative AI. Let's understand the differences between these three with some Lego analogy. First up, we have traditional software. It's like you're following a strict Lego manual. You know exactly how many bricks we use, where they go, and what the final house will look like. There's zero room for creativity. The house will always look the same because you're following step by step instructions, just like traditional software follows hard coded rules. Now we move on to the middle. Here you use discriminative machine learning. You have seen lots of Lego houses before, and you have learned to recognize what makes them different. One has a red roof, another has a blue door. You're not creating something new, but you are really good at spotting the differences and classifying them based on what you have learned. Think of it as your teaching model to say, this is a house with a red roof. That's a house with a blue roof. It's smarter than the traditional software, but still sticks to the script in terms of recognizing what's already there. And finally, here's where it gets wild: generative AI. Forget the manual. You're now building a spaceship or some crazy new Lego creation that no one's ever seen before. Generative AI isn't just following patterns or recognizing them, it's creating new things. It takes everything it has learned from houses, cars, whatever, and builds something completely original. The possibilities are endless. So, in Lego terms, traditional software sticks to the instruction. Discriminative ML can tell you what's what after it's learned the differences. Generative AI says, let's build something new from scratch. And that's how these three approaches differ. Generative AI is the most creative, while traditional software is the most rigid. Ready to see what else you can create with generative AI? Let's keep going. Now that we have explored the difference between traditional software, discriminative machine learning, and generative AI, let's take it a step further and see how generative AI really shines. Here is another analogy. We have a robo who has access to library. On the left, the robo has read a lot of books on dogs, cats, and chickens, and it has read enough of dogs, cat, and chicken books that it now has the ability to classify them into their own buckets. On the right, you have the generative AI robo, which has probably read every book on the shelf. So it has now developed abilities which are far beyond the traditional ML. Here you can see that it's great at not only classifying and organizing, it also goes beyond it. It can create entirely new things. But that's not all. Generative AI just doesn't create, it can also summarize, answer questions, and even extract key details from the data. It's like having the ultimate assistant that not only organizes your book but can also write new ones for you, summarize them, answer your questions about them. Generative AI is not just about creativity. It's about making sense of information and creating insights, all while being flexible enough to handle anything you throw at it. Now that we have explored all the amazing things generative AI can do, creating, summarizing, answering questions, extracting key information, etc., 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 it's pretty clear this AI assistant is a game changer. It's like having the ultimate sidekick that can handle pretty much anything. Well, a lot of things. We have to know the limitations as well. And just when you think generative AI can do more, it might even help us tackle the age old question, why did the chicken cross the road? Well, generative AI could come up with infinite answers, and some of them are for a change of scenery, to get to the other side, obviously, or maybe to avoid being classified by traditional ML. Awesome. Now we have covered or introduced generative AI, what it can do. Let's explore this question. Can it replace traditional ML? The short answer, not completely. While generative AI is incredibly powerful for tasks like creating content, summarizing data, or handling unstructured data like text and images, traditional ML is still the go-to for classifying, predicting, and working with structured, domain-specific data. Key differences: traditional ML best for sorting, classifying, and making predictions with structured data. Generative AI excels at creating, synthesizing, and handling unstructured data. The real world example could be fraud detection in finance industry, where traditional ML analyzes transactional patterns for known fraud. Generative AI creates new fraud scenarios to prepare for emerging threats. In short, they complement each other. Traditional ML is the reliable classifier, and generative AI is the creative problem solver. Together, they are a powerful team. Let's now understand what are pre-trained generative AI models. These are the real game changers in AI. These models like ChatGPT, Gemini, DALL-E, which you might have heard, are trained on massive amounts of data. Websites, books, code, images, using transformer architecture, which is a deep learning neural network. They are not starting from scratch. They have already learned patterns, which makes them incredibly efficient at generating content, answering questions, or creating visuals. Examples: ChatGPT for generating text conversations, answering questions, or creating images. Gemini from Google DeepMind takes it up a notch with multimodal capabilities, handling text and images. DALL-E, creating realistic images from text descriptions. So DALL-E is an image generation tool, and it is trained on several images using a transformer architecture to be able to create images from text descriptions as well. So let's understand its limitations. Here is the catch. These models are in real time. They can't fetch the latest news or trends unless retrained. So if you ask ChatGPT about yesterday's news, it won't know. What's the solution? It's RAG, or Retrieval Augmented Generation. RAG builds the gap by combining these models with real-time information retrieval. It allows the AI to generate content while pulling fresh data from web or databases, giving you the best of both worlds, creativity and up-to-date accuracy. Why this matters? Pre-trained models are already powerful, but with tools like RAG, they become unstoppable, blending creativity with real-time relevance. The future isn't just about what AI can generate. It's about what AI and you can create together. After understanding pre-trained models, let's explore power of prompts and how they differ from basic Google search. What is a prompt? A prompt is like a specific command you give to generative AI model. You ask it to create something, solve a problem, or answer a question in a more detailed, customized way than a search engine would. It's like talking to an assistant who already has a deep knowledge, and it delivers tailored direct responses rather than just providing links. How is this different from search? Google search. While you use Google, it acts like a librarian. It scans the web and gives you a list of websites related to your search. You still have to click, read, and filter through the results to find your answer. An example would be searching for best Italian restaurants in New York gives you a list of websites, reviews, and locations. Generative AI prompts. When you give generative AI a prompt, it doesn't just give you a link, it creates a custom response based on everything it learned. Instead of searching, it's like having a conversation with an expert who gives you exactly what you need in one go. While search engines provide you with links to find information, generative AI prompts can take it to the next level by delivering ready made solutions or creative outputs that go far beyond what a simple search can do. As powerful as pre trained models like GPT-4 and DALI are, they're still built on generic knowledge. To get the most out of them for your specific industry or business needs, the key is fine tuning. So, what is fine tuning? Fine tuning is like taking a pre trained model and giving it additional training or a narrower, more specific data sets that aligns with your unique use case. It's the difference between a general purpose tool and one that perfectly suited for the job at hand. Think of a domain specific information you have and a model which fits to answer the domain specific information. That's one use case of fine tuning as well. Why is fine tuning important? Precision and relevance. Fine tuning helps tailor the model to your specific data so it can handle industry specific jargon, technical terms, or unique tasks. Example for fine tuning would be a model for legal documents to help it understand and generate content based on legal terminology. Higher accuracy. When models are fine tuned with right data, they deliver more accurate predictions or better results tailored to your domain. An example to be a fine tuned healthcare model that can generate more accurate medical advice than a generic one. Customizations for your business. Fine tuning allows the model to learn your specific style or requirements. An example would be fine tuning for e-commerce platform means the model can provide better product descriptions, recommendations, and customer support based on your products and customers. Why is this crucial? Pre-trained models are powerful, but fine-tuning gives you the ability to create solutions that are specific to your needs. Whether you are in healthcare, finance, retail, or tech, fine-tuning ensures the model understands your data, your language, and your challenges. Fine-tuning allows you to unlock the full potential of pre-trained models by making them work specifically for you, resulting in more accurate, relevant, and customized AI-driven solutions. So, where do we go from here? Now that we have covered the fundamentals of generative AI, pre-trained models, and the power of fine-tuning, the question is, where do we go? What next? Explore your use cases. Identify areas in your business or industry where AI can make a meaningful impact. Whether it's generating content, automating tasks, or offering personalized customer experiences, generative AI can revolutionize fields from healthcare to marketing, education, and beyond. Leverage pre-trained models. Tap into the potential of models like GPT-4, DALL-E, and Gemini. Use them to get started quickly with tasks like content creation, summarization, customer service, and more. Fine-tune for maximum impact. Fine-tune these models for specific industry needs to get them even more accurate and relevant results. Tailoring AI to your unique challenges ensures you get the best possible outcome, whether you are in finance, retail, or technology. The future of AI is collaborative. The next step is all about collaborating with AI, combining human creativity with expertise with AI's power to automate, generate, and scale. Together, we can redefine what's possible. Are you ready to start your journey? Generative AI is here, and the possibilities are endless. The key is to leverage it in a way that benefits your business and your creative process. Whether you are optimizing existing workflows or pushing the boundaries of what's possible, the future is in your hands. And with AI as your partner, let's build the next generation of intelligent solutions together. Thank you for being part of this session at GenAI Kitchen, where we make AI solutions not just accessible but truly impactful. If you're ready to explore how AI can elevate your business, shape your strategy, or collaborate on innovative use cases, we are here to help. Visit our website and let's start the conversation. Together, we can unlock AI's full potential and tackle your unique challenges. A final thought, and remember, technology doesn't have to be complex or boring. With the right approach, it can be exciting and fun. Here's to embracing lifelong learning and staying curious. Ciao.